We have now arrived at this idea that we want to split the cases in the training partition into buckets which are as pure as we can make them to be. Now, this notion of pure, we still have not concretized it. We have sort of made hand waving sorts of arguments to say this is pure, that is purer, etc. But we have not given an objective criterion for purity. And that's what we look at in this particular lecture. Okay, so we will do quantify the impurity of a node, and we'll just give you two examples of different ways in which we can do that, two numbers that we can arrive at. Okay, so let's say that we've got 1200 cases in the training partition, and the way we are going to do is, obviously we've already said we choose a predictor, a column, and then we choose a value, and then we split it based on which cases satisfy the criterion and which cases don't satisfy the criterion. And we also saw this example of one scenario and two alternative splits, right? So one option is to split like this, and then you end up getting two buckets in which the composition of the buckets is almost the same, in fact exactly the same as the original, whereas here you see the composition of the two buckets was extremely homogeneous. This was mostly normal and this was mostly fraudulent. Okay, and we preferred this. Now what we want to do is to say, for this tree I want to arrive at a number which indicates how good it is in terms of homogeneity, and for this tree I want to arrive at the same number, meaning the same indicator, and then use the numbers to say I prefer this over that. Okay, that makes it more objective, and also because in this case we are looking at it, we can say this is better, that is better, but in reality, while the tree is being constructed, it's the computer that's going to do the construction of the tree. Okay, so the computer is the one that has got to make the calculations and say it prefers this over that, and it uses two different criteria. You can specify when you run the program which criterion you want it to run. Okay. Now, the actual details of the criteria are not very important, but I'll just give you an idea of what it represents. Okay, so let's say we've got two different trees that yield these kinds of compositions for the same data, and earlier we said which one is better. Okay, and in fact, in the previous lecture when we looked at the details, it was not easy for us to say one is better than the other, because this node was pretty good, this node was okay, this was very good, this was decent, this was not at all great because the sample size is too small, and this one is not great because it's almost equal, right? So here also we had this node which was fantastic, this was also good, extremely homogeneous, this was also extremely homogeneous, but these two were kind of iffy. Of course, overall it does look like this is a much better tree, but we would like to arrive at a number for this and a number for this and say, therefore, this is better. Okay? There are two different approaches to quantifying the impurity of a tree. Okay? Not of an individual node. First we'll define it for an individual node, and then we'll blow it up to the entire tree. So two measures of impurity, and we could use either measure. One is called the Gini index. Okay, I used a picture to indicate Gini, but of course it's not Gini, it's Gini. And the other is called entropy. Okay, now you don't need to really worry about the details of either of these. I'll show you the formula and so on. But the whole idea is that it's able to convert our subjective or intuitive understanding of purity of a node and convert it into a hard number that we can use for comparison. That's the basic principle. Okay, so let's say that we've got a node in which there are 40 cases, 10 of which are buyers and 30 of which are non-buyers. Okay, so the way we are going to compute the Gini index is like this. M is the number of classes. In this case, there are two classes, buyers, non-buyers. So therefore, M is 2. And then we want to calculate the proportion of elements of each class. Okay, so clearly you can see 1/3 are buyers, 1/4 are buyers, 3/4 are non-buyers. Okay, so that's what we have. So this is all the information you need to compute the Gini index. So once you have that, the Gini index is calculated as 1 minus proportion square, proportion of one class square minus proportion of the other class square. Okay, so you get a number, 0.375. Okay, so that's a measure of impurity of a node. Okay, now suppose both these classes were exactly the same. Okay, we'll see that. So this is the formula written in a different way. 1 minus sigma k equals 1 to mp k square. Okay, you don't need to worry about this notation. Okay, so when the node is completely pure, which means P1 is 1 and P2 is 0, when all the cases are of one class. So for example, if instead of 10 buyers and 30 non-buyers, if it was 40 buyers, 0 non-buyers, okay, that's a completely pure case, which means what? That P1 is 1, P2 is 0. Of course, P1 plus P2 must always be 1. Okay, so if one of them is 1, then the node is completely pure. And when it's completely pure, for example, 50 buyers, 0 non-buyers, or 0 genuine, 100 fraudulent. These are just different examples. 0 high, 12 medium, 0 low. This is a case where you have 3 classes, not 2. But all of them are in this particular node are medium. Okay, so the computation would go, and its maximum when it's completely impure, which means equal, 25 buyers, 25 non-buyers, 50, 50, 4, 4, 4, whatever, right? So it's in each of these cases, in these cases, the Gini index would be exactly 0. Why? Because it's 1 minus P1 is 1, P1 squared is 1, all the others are 0, so it's 1 minus 1, it becomes 0. Okay, so when a node is completely pure, the Gini index will be 0. And when a node is completely impure, then the Gini index is not one single number. It depends on the number of classes. Okay, it basically turns out to be m minus 1 by m. So if m is 2, then the maximum Gini index possible is 1. When m is 3, the maximum Gini index possible is 0.67. Okay, so here are some examples of computations of Gini. Okay, so you have 50 of class 1, 0 of class 2, so it becomes 1 minus 1 minus 0 is 0. 25, 25, completely equal, it becomes 0.5. Or there are 4 classes, 30, 30, 30, 30. Okay, then it becomes 0.75. You can verify the computations. Okay, so let's apply this understanding to the earlier example we considered. Remember we said this split is completely useless, this split is pretty good. So we would expect that the Gini index for this should be very low, because remember 0 means completely pure. So this should be much closer to 0 than this is. Let's do the computations. Okay, so here let's say normal 500, fraudulent 100. So the Gini index here is 0.278. Okay, which is, it's a low number because obviously this node, even the training partition itself is highly homogeneous. It's like 1:5. Okay, but of course each of these two nodes also has a Gini of 0.278. Okay, now of course individual nodes we can calculate the Gini index based on the formula we used. But what about the Gini index for the tree as a whole? Well, in that case, it will be the weighted average of the Gini indexes of the leaf nodes. So in this case, there are 2 leaf nodes, each of which has 300 cases, and each of which has a Gini index of 0.278. So the weighted average is also going to be 0.278. Okay, so the Gini index for this entire tree is 0.278. Now we expect, and therefore the split didn't do any good because it didn't reduce the Gini index at all. At the root node it was 0.278. After you did the split, it is still 0.278. So it provided no improvement, which we already knew. Okay, now the second split, look at the Gini index, right? This is 403. Okay, so the combined Gini would be 493 times 0.01. So this, the Gini index of this node is 0.012. Okay, which is very close to 0 because it's almost entirely pure. So it would be 3 divided by 493 is P1 and 490 divided by 493 is P2. Okay, and then this one has 10 divided by 107 as P1 and 97 divided by 107 as P2. Okay, so if you compute the Gini for this, it will turn out to be 0.012. For this, it would be 0.169. And then we take the weighted average. Weight this Gini by 493, weight that Gini by 107, and the total combined Gini comes to 0.04, which is much lower than what we got for the earlier one, which was 0.278. Furthermore, remember the Gini for the root node was 0.278. And this split made the combined Gini 0.04. Okay, it reduced the Gini or reduced the impurity considerably. Okay, so we got from a level of impurity of 0.278 to a level of impurity of 0.04. That is why we would say that this tree has a Gini of 0.04. The other tree had a Gini of 0.278, so this is better. So in the computer, at the time it is trying to build the tree, if it has to compare, should I do this split or should I do the second split? It's going to compute the Gini for the two splits and say, hey, the second one is much better, so that's the one I'm going to do. Okay, so that is, it is applying the Gini index as a criterion when constructing the tree. So effectively what the computer is doing is it's saying, here I have at the root node, I have the entire training partition and I have many possible ways in which I can split the training partition, meaning I can choose many different variables, many different predictors, and for each predictor I can split at different values. It's going to compute the Gini index for each of those and then choose the one that gives the highest Gini index. Okay, so clearly we can see that this is the better one that it should prefer. Okay, entropy is another such measure of impurity. In fact, I won't even go through the details, but it's just a different way of computing. And what we really want to do is to decrease the entropy, just like we tried to decrease the Gini index. Okay, the computation of entropy is this, don't worry about it. But the good thing about entropy is that its minimum value is always 0. The maximum value is always 1. Whereas for Gini, the minimum was always 0, but the maximum was m minus 1 by m. Okay, so this is a nicer way to look at it. 0, 1, doesn't matter whether it's 2 classes, 3 classes, 10 classes, doesn't matter. Okay, so entropy for the first split, again, at the root node is 0.65, and we know that the first split does no good at all. So the combined entropy is still 0.65, whereas for this one, for the second split, the root node entropy is 0.65, but after the split, the resulting tree has an entropy of 0.12, and therefore, using the criterion of entropy, it is still the better tree. Okay. Now you don't need to worry about how entropy and Gini are computed and so on. The most important thing for you to understand is that these are ways of quantifying in a very objective way the impurity of a node. Okay, and to lift that up to the impurity of the whole tree, you just take the weighted average of the leaf nodes. That's it.